Now, we have already seen that friction does negative work on a system and hence transfers energy out of the system. Friction is not a conservative force. So let's take a closer look at friction. Okay, so let's consider our system a rigid object on an inclined plane, inclined in an angle theta. In the absence of friction, there are two forces that act on the object, the force of gravity and a normal force perpendicular to the surface of the plane. Now, the force of gravity has a magnitude of m times g and is directed in the negative j hat direction. And so we write negative mg j hat. Now notice that one component of the gravitational force is perpendicular to the plane and cancels or balances the normal force, while one component of the gravitational force is unbalanced and points in the direction down the plane. So we can choose unit vectors, a unit vector u hat in the direction up the plane, and a perpendicular unit vector to u hat, v hat, in the same direction as the normal force. And so we can rewrite the components of the gravitational force in terms of the uv coordinate system, so that we have a component parallel to the plane with a magnitude of mg times the sine of theta. And this is in the direction of negative u hat. And a component perpendicular to the plane with magnitude mg cosine theta in the direction of negative v hat. And so this is negative mg sine theta u hat minus mg cosine theta v hat. And in this case, the normal force, which is balanced by this component of gravitational force, must have the same magnitude, which is mg cosine theta, and is directed in the positive v hat direction. Now, friction is an interaction between the surface of the object and the surface of the plane, and so friction is related to the normal force. The magnitude of the force of friction, which I'll denote with a lowercase letter f, is a constant mu times the magnitude of the normal force, where mu is called the coefficient of friction and is a number greater than 0 but less than 1. Magnitude of the normal force is mg cosine theta, and so the magnitude of the force of friction is mu times mg cosine theta. Now, the direction of the force of friction depends on the direction of motion. Friction always opposes motion. So suppose that we have motion in the positive u hat direction, that is up the plane. Then we have a displacement, delta r, that has some magnitude r in the direction of the unit vector u hat. Now, friction opposes motion, and so it is directed in the negative u hat direction. And so the force of friction is mu times mg cosine theta in the direction of negative u hat. And so we write negative mu mg cosine theta times u hat. And so the dot product of the force of friction with the displacement vector is negative mu mg cosine theta times r, or negative mu mg times r cosine theta. Now recall that the gravitational force is negative mg sine theta times u hat minus mg cosine theta times v hat. And so the dot product of the gravitational force with the displacement vector is negative mg sine theta times r, or negative mg times r sine theta, where r sine theta is the vertical displacement. And so this is the negative of the change in the gravitational potential energy. And so we have that the change in the kinetic energy is equal to the negative of the change in the gravitational potential energy minus mu mg times r cosine theta. That is the sum of the change in the kinetic energy plus the change in the gravitational potential energy is the negative of mu mg times r cosine theta, which is a negative value. That is, the change in the mechanical energy of the system is negative. The energy, rather, the system loses mechanical energy. So now suppose that we have motion down the ramp so that the displacement is some magnitude r in the direction of negative u hat. So this is negative r times u hat. Now again, friction opposes motion, so friction will be in the positive u hat direction. And so the force of friction has a magnitude of mu times mg cosine theta and is directed in the positive u hat direction. So the dot product of the force of friction with the displacement vector is mu mg cosine theta times negative r, or negative mu mg times r cosine theta. Again, the dot product of the gravitational force with the displacement vector delta r is the negative of the change in the gravitational potential energy, so that the change in the kinetic energy is equal to the negative of the change in the gravitational potential energy minus mu times mg r cosine theta. So the sum of the change in the kinetic energy plus the change in the gravitational potential energy is once again negative mu mg times r cosine theta, which is a negative number. That is, the change in the mechanical energy of the system is negative, and so the system loses energy. Now, when a rigid object is in motion, all of its particles are moving with the same velocity, and when a rigid object is in a gravitational field, all of its particles are experiencing the same force of gravity. And so the kinetic energy and the gravitational potential energy of the system are internal aspects of the system, whereas friction is an external interaction of the object with its environment, in this case, the surface of the plane. Now, conservative forces have two equivalent properties. The work done by a conservative force on a particle moving between any 2 points is independent of the path taken by the particle. Equivalently, the work done by a conservative force on a particle moving through any closed path is zero. So let's compare the gravitational force with the force of friction in terms of these two properties. Okay, so let's consider an object in the xy plane, where the y-axis is the vertical axis. And we'll consider a particle that moves from the origin to the point 1, 1. And first we'll look at the work done by gravity. So let's look at the path from the origin along the x-axis to the point 1, 0, followed by the vertical motion parallel to the y-axis from the point 1, 0 to the point 1, 1. For the first leg of the trip, we have the work done is the magnitude of the force of gravity, which is m times g, times the magnitude of the displacement, which is 1. Now the angle between the displacement vector and the force of gravity is 90 degrees. Cosine of 90 degrees is 0. And so the work done for this leg is 0. For the second leg of the trip, the work done is the magnitude of the force of gravity, which is m times g, times the magnitude of the displacement, which is 1. Now the angle between the displacement vector and the force of gravity is 180 degrees. Cosine of 180 degrees is negative 1. So the work done for this leg is negative mg. So that the total work done, which is the sum of W1 and W2, is 0 plus the negative of mg, which is negative mg. So now let's consider the path from the origin to the point 1, 1 along the line y equals x. The work done by gravity is the magnitude of the force of gravity, which is m times g, times the magnitude of the displacement. This is an isosceles right triangle, so the magnitude is the square root of 2. Now the angle between the displacement vector and the force of gravity is 45 plus 90, which is 135. Cosine of 135 degrees is negative square root of 2 over 2, so that the work done along this path is negative mg. So notice that the work done by gravity in moving from the point from the origin to the point 1, 1 is the same regardless of the path between the 2 points. Now consider the closed path along the triangle from the origin to the point 1, 0, followed by motion to the point, vertical motion to the point 1, 1, followed by motion along the line y equals x back to the origin. Then the work done on this closed path, the sum of W1 and W2 and the negative of W3, or W1 plus W2 minus W3, which is 0 plus the negative of mg minus the negative of mg, which is 0. So the work done along the closed path is 0. So once again, suppose we have an object in the xy plane, but in this case the vertical axis is the z-axis. And again, we consider motion from the origin to the point 1, 1. We'll look at the work done by friction. First, along the path from the origin to the point 1, 0, followed by motion parallel to the y-axis to the point 1, 1. For the first leg of the trip, the work is equal to the magnitude of the force of friction, which is mu times m times g, times the magnitude of the displacement, which is 1. Now the angle between the displacement vector and the force of friction is 180 degrees. Cosine of 180 degrees is negative 1. So the work is equal to negative mu mg. So now consider the second leg of the trip. The work done is equal to the magnitude of the force of friction, which is mu times m times g, times the magnitude of the displacement, which is 1. Once again, the angle between the displacement vector and the force of friction is 180 degrees. Cosine of 180 degrees is negative 1. So the work done is negative mu mg. So the total work is equal to W1 plus W2, which is negative 2 times mu mg. So now we consider the path from the origin to the point 1, 1 along the line y equals x. The work done is equal to the magnitude of the force of friction, which is mu times m times g, times the magnitude of the displacement, which is the square root of 2. Once again, the angle between the displacement vector and the force of friction is 180 degrees. Cosine of 180 degrees is negative 1. And so the work done is negative square root of 2 mu mg. Notice that this is not the same as for the path from the origin to the point 1, 0, followed by motion to the point 1, 1. So let's look at the work done on the closed path from the origin to the point 1, 0 to the point 1, 1, and then back along the line y equals x to the origin. The work on this closed path is equal to W1 plus W2 plus the negative of W3, which is negative 2 mu mg plus the square root of 2 mu mg, which is negative 2 plus the square root of 2 times mu mg, and this is not equal to 0. Okay, so in this lecture we've looked at potential energy, which is the energy associated with an object's position. Potential energy is stored energy that can be transformed into kinetic energy. We have looked at two types. Gravitational potential energy is the energy that an object possesses by virtue of its position in a gravitational field. And elastic potential energy is the energy stored in elastic systems, such as springs. The mechanical energy of a system is the sum of its kinetic energy and its potential energy. And if the mechanical energy of a system is conserved, then the change in the kinetic energy is equal to the negative of the change in the potential energy. Conservative forces do not change the mechanical energy of a system, while non-conservative forces do. The work done by a conservative force is path independent, and the work done by a conservative force through any closed path is 0. The important equations from this lecture are the following. The force of gravity is equal to negative mg times j hat, and so the gravitational potential energy is m times g times y. The restoring force for a spring is negative k times x times I hat, and so the elastic potential energy is 1/2 kx squared. And if the mechanical energy of a system is conserved, then the change in the kinetic energy plus the change in the potential energy of the system is 0. Next time we'll look at thermal energy and heat. So I hope you have enjoyed the second lecture. Thanks for watching.